This video discusses the steady-state operation and steady-state analysis of the doubly fed induction generator-based wind generator systems. In many of the future lectures, we will be learning about the dynamic modeling and dynamic analysis of DFIG machines, leading to the controller design for the two converter stages of the DFIG systems. But before we could get there, we also need to have a complete understanding of the steady-state behavior and operation of DFIG machines. Things like how the DFIG machine operates in the supersynchronous and subsynchronous modes of operation, and how we are able to achieve a generator operation even under speeds less than the synchronous speed. What should be the rotor voltage, magnitude, and the phase angle and the frequency to be applied to achieve many of the control objectives. All of these can be understood by the steady-state phasor analysis, which is the focus of this video. Here is an overview of the Type 3 DFIG wind generator systems. The basic machine is the doubly fed induction generator, and it also has two back-to-back three-phase converters sharing this common DC link. The stator has balanced three-phase windings which are connected directly to the grid through a step-up transformer. The rotor also has balanced three-phase windings with a turns ratio 1:n with respect to the stator windings. The rotor three-phase windings through slip rings are connected to the output, the AC output of the rotor side converter, which feeds controlled current, variable frequency, usually low frequency currents into the rotor, with the primary objective of maintaining the rotor speed to be the optimal speed corresponding to this maximum power tracking characteristics. It can also provide grid support functions as needed. It can also do reactive power support to the grid. So in injecting the appropriate rotor currents, the rotor side converter either draws power from the DC link or feeds power into the DC link, depending on whether we are in the subsynchronous or the supersynchronous modes of operation. Then the role of the grid side converter is to facilitate that power transfer between the rotor windings and the DC link, and eventually from or to the main grid. It can also provide reactive power support independent of the rotor reactive power, and together these two can give a very wide range of grid support and ancillary functions. So we will be doing the steady-state analysis using the per phase equivalent circuit of the DFIG machine. The per phase equivalent circuit corresponds to one given slip value, slip S. So you will see that in the per phase equivalent circuit, several of the parameters like the effective rotor resistance or the rotor leakage inductance, or the voltages applied from the rotor side converters, those will be defined with respect to the operating S, and that forms the operating condition for that particular analysis. The per phase equivalent circuit can be derived from the basic principles of operation of induction motors, which is very similar to those of the transformers. So this kind of per phase equivalent circuit can be very useful in fully understanding the steady state operation using phasors analysis. Okay, I should also mention a note about the conventions used here. Many of these dynamic models and control techniques like the field-oriented control, those were developed for motor drives, meaning the machine is operated in the motoring mode. So for example, the power coming from the grid, power drawn from the grid, converted to mechanical power in the motor would be considered as positive. So when these concepts were later extended to generator mode of operation, the same convention was continued. So in our generator case, the power would actually be converted from the mechanical side and fed into the electrical grid, and we call that as a negative power using the motoring convention. So that is something to keep in mind, and not to be confused when we see a negative value for the grid power. So that is because we're using convention based on the motoring mode. So as you are well aware, the operating principles of a three-phase induction motor is very similar to that of a three-phase transformer, and therefore the per phase equivalent circuit of the induction machine, in this case a DFIG, will also be very similar to the per phase equivalent circuit of a transformer, which is shown here. So here the primary winding of a transformer would correspond to the stator winding, and the secondary winding of the transformer would correspond to the rotor winding. The RS and this leakage inductance LLS, or its reactance omega S LLS, that is similar to the so they correspond, so the RS corresponds to the physical resistance of the stator windings, and this is the actual leakage inductance calculated from the leakage flux and the stator current. Similarly, on the rotor side, corresponding to the secondary side of a transformer, we have RR, which is the actual physical resistance of the rotor windings, and this LLR is the actual leakage inductance of the rotor windings. So all of the quantities shown here, they are represented on their own reference side. So the RS is referred to the stator, RR is referred to the rotor, and in later analysis we would choose to transfer all of them to the stator side or all of them to the rotor side, depending on which quantity we are actually trying to calculate. This branch is the magnetizing branch. LM corresponds to the magnetizing inductance, and so that is similar to the transformer, except that in a motor the LM is very small, and therefore the magnetizing current is significantly larger than what we see in transformers, and this is because of the need for fairly large air gap to allow the rotation of the rotor. So magnetizing currents in the range of 20-30% is not unreasonable, whereas for a transformer the magnetizing current is usually within the 5 or maximum 10% of the rated current. Okay, and then the electrical quantities like Vs, this is a phasor, and this corresponds to the applied stator voltage, which is same as the grid voltage, and Is is the phasor corresponding to the stator current. And notice, following the motoring convention, Is is defined going into the stator. Similarly, on the rotor side, we have the rotor current IR phasor, and the VR is the applied voltage from the rotor side converter, again in the phasor domain. Okay, so one of the main difference between the equivalent circuit corresponding to the transformer compared to the equivalent circuit that we are interested in here, which is the induction machine, is how we represent is this rotating structure. In a transformer, we don't have the rotating structure, so we will remove this and put a primary winding here and a secondary winding here, and all of them will be at the same frequency. But what we have here is the rotating structure. This corresponds to the stator windings, and these are the rotor windings, but this is actually rotating, and that is indicated by putting this explicit structure here. And the rotor is rotating at a speed given by omega r radians per second. Okay, so as I said, the rotating structure as opposed to the stationary windings in the transformer, this introduces several differences between transformer and the induction machines. First and foremost is in the transformer, the frequencies of all the voltages and all the currents in both the primary and secondary or any other windings, they're exactly the same frequency. same as the applied, say, the grid frequency. Whereas in the DFIG case, in the induction machine case, all the quantities on the stator side, they are at the grid frequency omega s, whereas all the quantities on the rotor are at a different frequency. Okay, it's omega slip. So omega slip is the difference, is omega slip equals omega s grid frequency minus omega r the rotor frequency. The reason is when you apply balanced currents in the stator windings, it creates a rotating field that rotates at the velocity of omega s. Okay. So the frequency of rotation, or the speed of rotation seen by the stator windings, is the full omega s. But in the case of the rotor windings, since the rotor windings are housed on the rotor, which itself rotates at the speed of omega r, the frequency seen, so the flexes that cut the rotor windings, they are at a speed given by it's a relative speed. So it's a difference between the omega s and omega r. Omega s minus omega r is the speed that the rotor windings see the flex or the magnetic fields created by the stator windings rotate at. Therefore, the induced voltages on the rotor winding is exactly at the difference speed, which is the omega slip, omega s minus omega r. So you'll see that the IR as well as the VR that we need to inject from the rotor state converter, they, at least in steady state, will be at the frequency corresponding to the omega slip. So that is one of the key differences brought about by the rotating structure. The frequency of the stator side quantities they are all like Vs, Is, and the magnetizing current. They are all at omega s radians per second, whereas the frequency of the rotor side quantities are at omega slip. Now S, the slip S, is the per unit omega slip. So it is omega slip divided by omega s. So therefore we can write the rotor side quantities frequency as S times omega s as well. Okay, then we consider the voltage magnitude on the rotor windings. So if you recall from your very basic electromechanical courses or the machines courses, you may recall that the induced voltage in a conductor, E, is given by BLU. E equals BLU, where B is the flux density, L is the length of the conductor, and U is the relative velocity between the conductor and the magnetic field, or the flux density B. So the key word is the relative velocity. So in the case of the rotor windings, they are themselves rotating at omega r. The magnetic field created by the stator is rotating at omega s. Therefore the relative velocity depends on the difference, omega s minus omega r, or the omega slip. So therefore the rotor voltages are proportional to omega slip, versus the stator voltages being proportional to omega s. So there is a scaling of the voltage by this factor s. So one is omega s, other is omega slip, and omega slip is s times omega s. So there's a scaling of factor s. So if you also consider that the turns ratio, the physical turns ratio between the stator windings and the rotor windings is n. So 1 is the n, is the stator to rotor turns ratio. Then the net rotor voltage is scaled by a factor ns compared to the stator voltage, where n of course is the physical turns ratio, and s is the given value of s under which the per phase equivalent circuit is being drawn. Okay, so you may be tempted by looking at this voltage relationship to somehow represent this rotating structure as a transformer, as an ideal transformer of turns ratio n times s, because the secondary voltage is ns times the primary voltage. Therefore, you may indicate the turns ratio as 1 is the ns. But that is not quite correct because of the current relationship. So in particular, the primary current is not ns times the or the stator current is not ns times the rotor current. So unlike the voltage magnitudes, the current magnitudes are not scaled by the slip value s. So that is because if you follow the transformer principles of calculating the primary current, so when there is a secondary current, you have an equivalent current on the primary that goes to cancel the mmf produced by the secondary current, so that the flux in the core is simply determined by the applied voltage by Faraday's law, or the flux corresponds to just the magnetizing current component. Okay, yeah, a similar thing happens in the case of induction machines as well. So when there is a rotor current, there is a corresponding stator current. You can call that as the reflected rotor current component of the stator current, which goes to cancel the mmf produced by the rotor current. However, there is no relation for this current on the slip. So what really happens is this mmf cancellation is viewed in the air gap. So the flux produced by the rotor, so the rotor currents are at the slip frequency as we established earlier. Okay. So the rotating field due to the rotor currents in the air gap is at omega r, which is the speed of the rotor itself, plus the omega slip, which is the frequency of the rotor currents. So the field as seen in the air gap is the sum of the rotor speed plus the frequency of the rotor currents themselves. So that's omega r plus omega slip, which is same as omega s. So they are at the same frequency. The stator produced mmf, or the stator currents that goes to cancel the rotor mmf, is going to be just at the same frequency as omega s, and there is no additional scaling of s in calculating the current magnitude as seen at this stator. Okay. So it is just like in the transformer, the stator currents are scaled only by the turns ratio and not by the value of slip s. So therefore, when you refer any current from the stator side to the rotor side or vice versa, you scale the current magnitudes only by the physical turns ratio n and not the value of slip s. That is a very important distinction between what happens for the voltage versus what happens for the current. So that is the main reason why we cannot simply call this rotating structure as a transformer with a turns ratio of n times s. Because that is valid only for the voltage and not for the current. So for the same reason, how the impedances transfer from one side to the other side also differ between the transformer case and the induction machines case. In the transformer case, the impedance is scaled by the square of the turns ratio. So for example, if Rs is the primary side resistance, and if you want to transfer to the secondary side, it will be Rs times n squared, where 1 is the n is primary to secondary turns ratio. And in the case of the induction machine, since only the voltage scales by ns and the current scales only by n and not by s, the impedance now does not simply scale by the square of ns. So that is an important distinction to be remembered, and that has big implications on the power processed by the stator and the rotor windings, both the active power and the reactive power. Okay. In particular, in the case of transformers, both the active power and the reactive power at the primary and the secondary are equal, except for losses in the resistances and the reactive power losses in the leakage inductance and so on. Whereas in the case of induction machines, these two can be very, very different. Okay, so the key thing to remember is when going from, say, the stator to the rotor side, the voltages scale by n times s, whereas in going from the rotor to the stator, it scales only by n and not by ns. So s does not appear in that transformation.